Example 4.3. This is a two vehicles linear kinematics problem. It says that when the traffic light turned green at a traffic junction, a car A moved off from rest with a uniform acceleration of 0.4 meter per second square. 2 seconds later, a motorbike B starts off from rest from the same junction with a uniform acceleration of 0.8 meter per second square. Assume that A is traveling in a straight line with B following along the parallel path. First, sketch the VT graph for the motion of A and B. B. How much time is required for the bike to catch up with the car from the instant B began moving? So first and foremost, we need to sketch the VT graph for vehicle A and bike B. Now, a VT graph, again, velocity time graph. Since this is a uniformly accelerated body, we know that the VT graph is a straight line. So let's take a look at what other information given in this problem. We know that the car has an acceleration of 0.4 meter per second square. For the bike, it is 0.8, double the acceleration of the car. So in order to sketch the VT graph of the car, we know that it starts from rest at time 0. Now, in order to plot a line, we need 2 points. So we got the first point for the car. Next, we know the acceleration formula is equals to final velocity minus initial over t. So in order to get the other point whereby we can plot the line, the VT line of the car, we just apply the acceleration formula and assume time of 10 seconds. Substitute in this 10 seconds into the formula, we get the velocity of the car at 4 meter per second. And there we can actually put the next point. And with 2 points, we join the line and we get the VT graph of the car. So in the same spirit, we will do this for the bike as well. We know that the bike starts from 2 seconds later. So applying the same approach with t equals to 10 seconds and throwing that into the acceleration formula, we know that the bike will have a 8 meter per second after 10 seconds period. So again, 2 points, draw the line. So this completes the VT graph plotting for the car as well as the motorcycle. So the second half of part A asks us to indicate on the VT graph the instant when the bike caught up with the car. So this is the VT graph again. When the traffic light turns green, the car accelerated at 0.4 meter per second square. 2 seconds later, the bike gave chase with an acceleration of 0.8 meter per second square. So, at which part of the VT graph did the bike actually caught up with the car? Is it at this instant where the two lines intersect? Let us take a look. At this instant time t, when the two lines intersect, from the VT graph, we know that they share a common velocity v. Now, does this v indicate that the bike actually caught up with the car? The answer is no. The same v means that on the speedometer of both vehicles, it is showing the same velocity or speed. But it doesn't mean that the bike actually caught up with the car. So, when will the bike actually caught up in the car along the VT graph? Let's take a look. Now, at certain time t, the bike will actually be able to catch up with the car. And at that instant, the displacement of the bike must be equal to the displacement of the car. Now, at this instant t, they will have different velocity data, but we know that the area under a VT graph will indicate the displacement traveled. This is the displacement traveled by the car. This is the displacement traveled by the bike. So for both vehicles to meet side by side, the displacement must be equal. That implies that the displacement of the bike must be equal to the displacement of the car. And from the VT plot, we see that the blue area must be equal to the red area. So this is just a simple area of a triangle. We can establish this equation. Half times t minus 2 times bike, because the bike started 2 seconds later, must be equal to the displacement of the car, which is half times t times the velocity of the car. Now with this relationship established, we can now solve the time where the bike actually caught up with the car. Looking at this equation, we realize that there are three unknowns: time, velocity of bike, and velocity of car. So how can we solve this equation? Well, we have the acceleration data. We know that the acceleration of the bike is 0.8 and the acceleration of the car is 0.4. And using the acceleration formula, we can actually express velocity of bike as well as velocity of car in terms of time. And with that, we substitute back into our original equation that we have established, and we simplify. And through simplification, we will arrive to a quadratic equation. And how do we solve a quadratic equation? Well, all we need to do is to apply the quadratic formula. So by applying the quadratic formulas with the known values, we will arrive to two answers. Time equals to 6.83 seconds or 1.17 seconds. So which one should we choose? Well, we know that the bike started 2 seconds later after the car took off. So obviously, the time t must be more than 2 seconds. And henceforth, time is equals to 6.83. Question B asks us, how much time is required for the bike to catch up? Henceforth, the final answer is, the time taken for the bike to catch up with the car is 6.83 seconds minus 2, which is 4.83 seconds.